Zoom recording. Right, so today we're going to be talking about Coulomb's law. Well, okay, let me actually start by giving you some info. So my name's Sam Blitz. You guys should already know that. I hope you've seen the syllabus. Yes, there is discussion today. My name's Sam Blitz. Don't call me Dr. Blitz. I don't have a doctorate. Don't call me Professor Blitz. I'm not a professor. I'm a grad student instructor. Call me Sam. My email address is shblitz. There it is. At ucdavis.edu. I have office hours posted on Canvas. I have there's a whole bunch of information posted on the front page of Canvas, which is your syllabus. My office hours are going to be on Wednesdays from, I think, 10 to 11. And the reason for that is because of when the homework is going to be due. Again, go read the syllabus. It has a whole bunch of information, a whole bunch of links for you to click on it. It'll answer every question that you have. Just one thing that you guys should know, having showed up. So there are daily quizzes in lecture at the beginning of the first 5 minutes of lecture or so, and you'll be able to start it at 5 minutes before lecture start. There will be a quiz on Canvas. I'll send out an announcement regarding how that's going to be handled. It's really easy. Just click on the link and then it'll take you to a quiz and it'll be multiple choice and all that. But the point is this coming quiz, the one that will be on Thursday, that will include syllabus questions. So keep that in mind, read the syllabus. That's basically your homework for today. Read the syllabus, you'll be fine. Right. So we don't have a whole lot of time and I have like 11 pages of notes to get through. So let's jump right in. Right. So we're going to talk about Coulomb's law today. Oh, and for the record, we're covering chapters 1.1, 1.2, and a part of 1.3. Yeah, well, the quizzes will be open note, open book, whatever. Yeah, it's open everything, just not open collaboration. Sections 1.1 through 1.3 is what we're going to cover today, or at least I'm going to hope to. So first, let's talk about forces. So hopefully you guys remember from 9A. There are some forces that you may be familiar with. These are things like the contact force, the spring force, the tension force. These should all be familiar terms. Friction force, and the gravitational force. And feel free, by the way, to type out questions if you have them. I won't necessarily answer all of them, especially if I don't have time, but I will do my best to at least like quickly answer questions, or I'll tell you, hey, stick around afterwards and we can talk about it. Because I know that I am going to go pretty quick. So anyway, so all of these forces were talked about in 9A, but the important point is that with the exception of the, or besides the, with the exception of the last one, i.e. the first four, if you check the syllabus and go to the approximate course schedule, that's where it is. It's sections 1.1 to 1.3, and that'll always be there. The first four require contact between the two objects. So if you want a contact force, obviously that requires the two objects to be touching. A spring force, you have to have a spring touching the thing. Tension force, you need a rope tied to your object. Friction force, you need the object sliding on the thing. The only exception is that the gravitational force acts at a distance. And that's kind of important and interesting that it's unlike every other force that you see in 9A. And so let's take a slight detour and talk about Newtonian gravity for a minute. Hopefully you guys covered this in 9A. I know I did in spring quarter. At least I think I did. Jeez, it's been so long. But we're just going to take a detour to Newtonian gravity. So hopefully remember, that the force of gravity on an object of mass 1, from an object of mass 1 on an object of mass 2, the formula for that looks something like negative g m1 m2 divided by r squared times r hat. So again, as a quick refresher, if you have an object m1 over here and an object m2 over here, this distance, or that vector, is the vector r. It has length r, and the unit vector that points in that direction is r hat. So this formula completely describes both the direction and the magnitude of the force. R hat is the unit vector that points from m1 to m2. And in this case, there were a few things that we had to know. G is just a number. It's 6.67 times 10 to the minus 11th Newton meters squared per kilogram squared. This should all be reviewed, by the way. M1 is the mass of the object exerting the gravitational force. M2 was the mass of the object feeling the force. R is the distance between M1 and M2. By the way, sorry if my handwriting gets sloppy. It should be readable, and I make a point to make my lecture notes more readable than my live lecture notes. So if you can't follow what I wrote, go back and look at the lecture notes later, and it should be more clear. And R hat is the unit vector from R1, or sorry, from M1 to M2. So that's what all of those things mean in the formula. In the lecture notes that I'm going to post online, I do a quick detour of how to actually use these coordinate systems. But again, you guys have all taken this class before. You've all done coordinates and vectors and things like that. You've all taken both math, all of the math required, and you've taken all of the you've taken 9A and 9B. So none of this should be particularly new to you. This is just a quick refresher on what the formula is for Newton's universal law of gravitation. Now, the interesting thing, and the reason I brought up Newtonian gravity, is that Coulomb's law seems to be similar, very, very similar to Newton's law, or Newton's universal law of gravitation. So let's go back to Coulomb's law now, keeping in mind what the formula is for Newtonian gravity, and we'll start to see similarities. So first, we need to outline some properties of Coulomb's law. Coulomb's law is basically the electrical equivalent of Newton's universal law of gravitation. Newton's universal law of gravitation tells you what the force is between two masses due to gravity. Coulomb's law will tell you what the force is between two things that have charge. So this is the electric force, and it is both attractive and repulsive. So that's a difference between Newton's gravity, Newtonian gravity, and Coulomb's law, that Newtonian gravity is only ever attractive, whereas it seems like, and from experiment we can determine this, that the electric force seems to be attractive or repulsive. Also, again, from experiment, one can determine that the force depends on electrical charges. And I'm going to explain what all of these mean in a minute. I'm just outlining some details about Coulomb's law. So, just like how Newtonian gravity depends on the masses, Coulomb's law tells us that the electric force depends on the electrical charges. Think of electrical charge, or you can think of mass almost as gravitational charge. So Coulomb's law cares about electrical charge. So the electrical force can be attractive and repulsive, so there has to be two different criteria here. So if you have two of the same type of charges, we observe in the lab that you get a repulsive force. So if you have two things that have the same type of charge, they repel each other for some magical reason. And if you have two objects that have different types of charges, then you get an attractive force, again, for some magical reason. This is just things that you could observe in an experiment, in the late 1800s. You just have things that seem to magically attract and repel each other, and there's two types of things that attract, or the two types of things. When they're different, when you have the two different types of things, they attract, and we have the two same type of things, they repel. That's just something that you could notice in a lab 250 years ago. So rather than just saying that there's charge type A and charge type B, all we do is we just call them both the same type of charge, but one is positive and one is negative. And so that just simplifies our understanding a little bit. Whereas for gravitational charge, mass, you only have positive mass. There's no such thing as negative mass. The difference here is that there are two different types. There's the kinds that attract each other, and there's the kinds that repel each other. And so we have to use this idea of a negative quantity, and it makes it really easy. It makes it like very mathematically elegant. And so with this construction, saying that type A are positive charges and type B are negative charges, we get the statement that you may have heard, say in high school physics: like charges repel, and unlike charges attract. This is to say, if you have two of the same type of charge, i.e. both positive or both negative, then you get a repulsive force. If you have two of different types of charges, i.e. one positive and one negative, then you get an attractive force. Now, what else can we learn from just doing experiments in a laboratory? Well, turns out a lot, actually. We can also find that the force is inversely proportional to the distance between the charges. That's just something that you can measure, right? You can measure the force on an object just by like attaching a spring to it and measuring how far it stretches. And if you put two springs on two objects that are either attracting or repelling each other, you can measure that the force gets weaker as the distance gets larger. Further, we can also learn that the force is proportional to the product of the two charges involved. So if you double the amount of charge on one of your things, let's say you have two objects, two steel balls, say. One of them has charge A, one of them has charge B. There will be some force between them, whether attractive or repulsive. But if you then just magically make one of those steel balls have twice the amount of charge, say now you have charge 2A and charge B, now the force will be double. And if you multiply the charge on both of them by 2, so you have charge 2A and 2B, the force will be quadruple. So we see that the force is not only inversely proportional to the distance, it's also proportional to the product of the two charges. Just like Newtonian gravity, it's proportional to the product of the masses. So with all of this laid out, we can actually write down a formula, or at least a rough formula, for the force. The Coulomb force, I'm going to call it F sub c, from object 1 on object 2 has a magnitude that's proportional. Doubling the mass of one of them makes the force. No. So we're not talking about mass anymore. We're talking about charge. Doubling the charge of one of them doubles the force makes the force twice as large as the original. Doubling the charge on both of them, because you're doubling the charge on one and you're doubling the charge on the other, that's 4 times the product is 4 times larger. So that would be quadruple the original force. Right, so putting all of this together, the force, the Coulomb force from object 1 on object 2 would be proportional to the product of the charges divided by the distance squared. And I actually don't think I mentioned this. I meant to mention this. The force is inversely proportional to the distance squared between the two objects. So if you double the distance, the force reduces by a factor of 4. If you triple the distance, the force reduces by a factor of 9. And that can be measurable. You would just plot it and see what shape it takes, right? So just to make things easier, we start assigning numbers to these things. So a thing can have an amount of charge, just like it can have an amount of mass. So we call the amount of charge that object 1 has, we just give it a variable name. We call it Q1. So lowercase q, or uppercase Q, as it were, are usually the letters that we use to denote charge, just like how we use M for mass. Don't ask me why Q is used, I don't know. Object 2, similarly, would have charge Q2. And so, just like mass, a thing would have some amount of mass in some units, right? This pen has, a mass of maybe 100 grams, and so it's 100, the number is 100 and the units are grams. So we need the units for charge. How do you figure out how much charge something has? Well, it's measurable, so you just need to set a standard. How much is 1 unit worth? It turns out that the French, I think Coulomb was French, just decided on a quantity, and it's called the Coulomb, named after Coulomb, the guy who came up with this law. And that is the SI unit that we use, and it's abbreviated C. So what we would have is that the force, the Coulomb force, named after the same guy, from charge Q1 on charge Q2, I don't need to write the word charge out, is equal to, and I'll explain where all these terms come from, K, so that's just the product of, or that's just the constant of proportionality, times Q1 times Q2, that's the product of the charges, divided by the distance between them squared. We give that letter, we use the letter R for that, just the same as we did for gravity. Now this is a vector because it's a force, so we need to figure out what direction it's in. Now the key here is that we know the force is attractive or repulsive, meaning that it's always directly towards or directly towards or directly away from the object that's sourcing the force. So that's very similar to the gravitational case. In the gravitational case, we figured out, sorry, let me scroll up to, there we go. We figured out that the direction is in the r hat direction. In fact, it's in the negative r hat direction. That's not what I meant to do, because it's attractive. But we want the force to be repulsive when they have the same sign. So all we do is we multiply this by the unit vector r hat, which again points from object 1 to object 2. Now, note that we do not have a minus sign. In fact, we have a plus sign there. And the reason for that is, imagine that both Q1 and Q2 are positive, i.e. they're both they're both positively charged. That means that they should repel. And so we would want the force to point away from object 1. We would want the force on object 2 to point away from object 1. And the vector r hat already does that. Whereas if we had a minus sign built in, it would point towards object 1. Whereas if the charges were opposite, if one is positive and one is negative, then the product of their charges has a negative sign attached. And so that will make the force attractive. This number K, by the way, you can just measure. Sure, yeah. So the idea is that r hat, I'll just draw this. So here you have Q1, here you have Q2. R hat points this way, right? It points from R1, or from Q1 to Q2. And so if the charges are the same, i.e. if Q1 and Q2 are both positive, then when you multiply them together, you get a positive number. And so you would want the force to point away from Q1, so you would just multiply it by R1, and everything's fine. However, if the force should be attractive, well, that means that the charges have different signs. And when you multiply two things with different signs together, you would get a negative sign, right? And so we would want the force to be attractive, i.e. towards Q1, and that's precisely negative r hat. So the direction, whether it's attractive or repulsive, is taken care of by the sign of the charges, Q1 and Q2. All r hat does is it tells you the actual direction, whether it's up or right, rather than right or left, if that makes sense. And we can talk more about it after lecture if we need to, but I do want to move on because, again, we have a lot to do. By the way, the number K, it's just an experimentally measurable number. It's 9 times 10 to the 9th Newton meters squared per Coulomb, or sorry, Newton meters squared per Coulomb squared. Now, just as a quick aside, some textbooks and some people use a different constant of proportionality. It's like the same number, but it's just written a different way. they use 1 over 4 pi epsilon naught rather than k. So everywhere where you would see k in my writing, they would have 1 over 4 pi epsilon naught. And then epsilon naught is just whatever number it has to be so that 1 over 4 pi epsilon naught matches k. There's a good reason to do so, but for our purposes, we're not going to. Now, by the way, using this formula, there's a good example that's worked out in the textbook. Yeah, it's basically from Gauss's law. There's a good example that's worked out, sorry, not in the textbook, in a different textbook, and I've linked to it in the lecture notes. So after lecture, you can go through and you can actually click on that or type in that URL, and it'll take you to a worked example of calculating the force on an electron in a hydrogen atom. I'm not going to do that because I don't have time, but I think that you guys might get some use out of that. Again, it'll be in the lecture notes that are posted. All right. Okay, so that's the force. Now but we still haven't really explained what charge is, so let's talk about charge for a little bit. Properties of electric charge. Like so far, it's just a thing that makes things attract or repel each other. We haven't really understood it very well. So I understand it, but you guys might not, so I'm going to tell you some things. So first of all, it turns out, for very complicated reasons actually, that there exists a minimum fundamental charge. Sorry, minimum shouldn't be in quotes. Fundamental should be in quotes. Fundamental unit of charge. I.e., the smallest amount of charge that you can possibly have is not 0. It's 0, but then the next one up isn't infinitesimally close to 0. It's just some discrete number. That number, often denoted by the letter E, and E is not 2.718. It's this E stands for the charge of an electron. It's 1.6 times 10 to the minus 19th coulombs. That's the number that it is. That's the smallest amount of charge that anything can have. Turns out, as I said, this is the amount of charge that an electron has, just negative. It is due to quantum mechanics that the fundamental charge is what it is. Just as a quick point, though, electrons have negative E charge. They have this much charge but negative. Protons have exactly the same amount of charge but positive. Another fact, also for deep reasons, electric charge is conserved. I.e., you can't create or destroy charge. It just doesn't work. There are some processes, like beta decay, where you take a neutron, and it turns into a proton, a neutron, and an antineutrino. Don't worry about the antineutrino, it doesn't have charge. But the important point is that a neutron has 0 charge, a proton has +1 E charge, and an electron has -1 E charge. So even though you made charge, the net charge of the whole system always stays the same. I.e., there is a fixed amount of charge in our observable universe, and it will always be the same number. It never changes with time. That's what conserved means. Also, charges reside on substances, i.e. things have charges. And typically there are 2 types of substances that can have charges, or there are 2 types of substances and they have charges in different ways. There are conductors, which we will talk about a lot. And in conductors, charges are free to move around. So think of conductors as just like an empty room, and the charge can just wander about inside of it. And then there are insulators. The constant charge of the universe is just some fixed number. It's probably close to 0, but it's not something that we can know a priori. For insulators, the charges are fixed or locked in place. So in that case, think rather than an empty room that the charges can wander around in, think like you have charges just glued to a wall and they can't move. That would be an example of an insulator. So that's great. We hopefully, at least now, we have some basic idea. We have some basic idea as to what charges are and like what kind of thing they are. It turns out the basic or the typical source of charges in our universe are either electrons or the lack of electrons. And that's just how it works. And electrons have this much charge. So if a thing has more electrons than protons, then it will have some amount of negative charge, because the number of protons is the positive charge, the number of electrons is the negative charge, and they add together. So hopefully it's all kind of straightforward. Now we just have to start doing some more complicated applications, right? So first, what happens? What if there are more than one charge? There are more than two charges in a given system. How do they interact with each other? Like, because when there are two charges, you can just apply the Coulomb law, right? Just apply this and that'll be the force. But what if there's more than two? It turns out it's actually, like, it's a really straightforward question to answer. The total force on any charge is determined by adding the forces, or determined by adding all of the forces acting on it. This is just via vector addition, right? Forces are vectors, and you can add vectors together. So the idea is, if you have three charges and you want to figure out what the force is on one of them, you just find the force from, say, charge 1 on charge 3 via Coulomb's law, and then add to that force the force from charge 2 on charge 3. And that's the resulting force. Again, there's another example for this that will be in the lecture notes, but I'm going to skip over it again because we're trapped for time and we've only gotten through 2 pages. All right. So it turns out that adding up the force on a charge from a whole bunch of other charges, especially when there's a lot of charges, and generally there are a lot of charges in any given problem, like an infinite number generally, that's generally hard to figure out the force. But there's an easier way to handle it. And so we're going to talk about the electric field. So first we need to answer kind of a conceptual question. How does one charge tell another charge where it is? And by the way, we do this thing in E&M where we kind of just conceptualize charges as not like objects that have charge, but just like a clump of charge. Maybe it's just a clump of electrons or a clump of protons or whatever. And so when I say one charge tell another charge, I'm talking about a clump of one charge talking to another clump of charge. So how does one charge tell another charge where it is? And this is seems like a strange question, but it's, at the end of the day, it's reasonable, right? Because they're not touching each other. So, but the force on one charge depends on the location of the other charge. So how do they actually know? How do they communicate that information? It turns out that the charges don't tell other charges information. They tell the universe information, and then the universe tells every other charge information. And I'll elaborate more on that in a minute. But the takeaway is that the charges don't actually talk to each other. They talk to the universe, and then the universe talks back. So in general, a charge only knows about its own charge. And then what it does is it takes that charge info, and obviously we're anthropomorphizing here, but it takes that info about its charge, and it just sends information out. Think of it as like sending signals out in every direction. It just says, that way, hey, people over there, I have 5 coulombs of charge. Hey, people over there, I have 5 coulombs of charge. 5 coulombs of charge, 5 coulombs of charge. And it just tells everybody that there are 5 coulombs of charge here. Now, obviously, again, it doesn't do this explicitly, but it sends out a signal. Now, just like everything else, and as you guys saw in 9b, whenever any sort of information is sent out in all directions from a single point, like think a wave, the signal gets weaker as it spreads out, as it gets further away. So if a distant charge receives that signal, like say you have a charge where I am and then a charge in New York, when the charge from New York finally hears the, hey, I have this much charge, it'll be really quiet. Yeah, they are transmitted uniformly. They're transmitted spherically, actually. When the charge in New York finally hears that message, it'll be very, very quiet, i.e. the strength of the signal is very, very small, and it gets smaller with distance. And so when the charge in New York finally receives that signal, which tells it how much charge, it has information about A, how much charge is there, but it also knows about how strong the signal is, because the signal that it receives is the strength of the signal. So it has information about both the strength of the signal, or rather the distance, which is related to the strength, and how much charge was initially there. And further, by setting up a few different charges, or by setting up a few different experiments, you can figure out what direction that signal came from. So just by one charge shouting into the void, hey, I have this much charge in all directions, every other charge will eventually hear that signal and will be able to tell from that signal how strong the force should be on it, because it knows how much charge is over there and how far away it is, and it'll know what direction the charge was, or the signal was coming from. So it can figure out which direction. So the force acting on it is determined by that signal, because the force needs both the magnitude and both the magnitude and the direction, right? So the point is the charges don't talk to other charges. They just they just shout out into the void. But there are other charges over there, and those charges will overhear that screaming from charge 1, and it'll be affected by it. And I'll make it formal why we say it talks to the universe, not the other charges. But there is a real sense that happens. So first, so there's all of this business. This is kind of an analogy, but this is all written up in more detail again in the lecture notes. But the point is that this thing happens, and so you might ask, okay, well, when do the charges do this? Do they do it when they first pop into existence and then it's done? No, it turns out that these electrons are shouting into the void constantly. They're just always sending out signals. There's this much charge here. There's this much charge here. There's this much charge here, just forever. And so at any given instant in time, you can look at anywhere in the universe, whether there's a charge there or not. You can look at that point and you can figure out, what was the signal that I heard, that I would hear from that charge over there that sent out that signal? Even if it was 1 billion years ago and it's 1 million light years away, you could figure out how much charge is there, because it's been sending it out for all of eternity, for the entire time that charge has been there. So really, that's, rather than just being a single pulse that the charge sends out as a signal, it's just a constant stream of information that permeates the entire universe. And so what I'm really saying when I say that the electron talks to the universe, what I'm saying is this, oh boy, I hate this bug. It's doing that thing where it thinks that it should be writing even though my mouse hasn't. Okay, this is gonna look really sloppy for a while, because right now my pen isn't touching the screen even though it's writing. So this is gonna look sloppy, and I apologize for that. It's a really annoying bug. It won't be in the lecture notes though. So the space permeating field or signal rather, is called, oh, is it fixed? Nope. It's called the electric field. Or rather, it's the electric field of the source charge. Again, sorry that this is happening. I hate when this bug happens. Just like some sort of weird calibration thing. Also, sorry about the existential crisis that kind of just comes with the territory. Okay, now my pen won't close again. Oh, it's working again. Excellent. Right, so it won't be sloppy. Right, so this electric field, this is the signal that passes through, or that this is what I meant when I was talking about the electron talking to the universe. The electron tells the electric field, which is basically that signal everywhere in the universe, it tells the electric field what to be. So the electron tells the electric field, tells the universe, the electric field needs to be this at all of these different locations. It turns out that signal does actually have a travel time. So if you start moving around the electron, or whatever your charge is, it will take time for it moving around to affect elsewhere. But we don't really need to worry about that, because we're talking about electrostatics, and because the travel time is really, really, really fast. Yes, it is the speed of light, in fact. Well, it depends on what medium it's in, but generally, yes, it's the speed of light. Now, the electric field carries info. It carries info about a number, i.e. the distance and the strength, and a direction, i.e. where did the signal come from? So that means it can be described by a vector, just like a force. So if the force, and by the way, all of these F's are going to be referring to Coulomb forces, so I'm not going to write the C's anymore. Wait, if the charge is information, then how can it have this speed of light? I thought info, no. So info can't travel faster than the speed of light. Info can travel at the speed of light, though. So if the force, say Q1 on Q2, the force from Q1 on Q2, that would be written K Q1 over Q2, or K Q1 Q2 over R squared times R hat. Then the electric field that comes from Q1 should be, well, it has to contain information about the strength, and it has to contain information about the direction. And so we can encapsulate all of that as this vector E, which would be written as K times Q1 divided by the distance from that charge squared, and the direction is R hat. And in this case, the source of the electric field is at the origin of the system. So again, there's another example that will be linked in the lecture notes, and it's just showing you how to calculate the electric field of an atom. Useful example. So the electric field is what it is it's basically a vector at every point in space. And in fact, when you hear physicists talk about fields, what they're really talking about is they're talking about a type of thing. In this case, it's a vector field. They're talking about either a number, a vector, a tensor, a spinor, whatever, that has a different value, potentially different value at every point in space. That's what a field is. So a vector field has a different value of its vector everywhere in space. And you can see that at different places, this value of R changes because you're a different distance from the source. And so the electric field at any given place depends on the distance, the magnitude of the force vector, the magnitude of the field vector. Wait, is the R hat the denominator, or no? It's R hat is not the denominator. It's multiplied by the numerator. Sorry. There we go. Right. Okay. So how can we visualize this? Because visualizing forces is easy. Visualizing the electric field might be more challenging. So let's talk about that. Visualizing forces is easy because you can just draw vectors, and that tells you the force. And by the way, this is going to be called the E field from now on. Sometimes I'll write like a little arrow over it to indicate it's a vector field, but either way, it's the E field. So at each point in space, there is a vector. So we can just draw a vector. We just draw a vector at as many points in space as we can, and that vector points in the correct direction, and it has the correct magnitude. So I'm going to give you an example of my best attempt to draw a vector at every point in space. So let's say that we have a positive charge in the middle. So we know that Q is positive, so it's going to point in the outward radiating direction because it points in the direction of R hat, and its magnitude should decrease as the distance gets larger. So close to the vector, you'll have a whole bunch of, or close to the charge, you'll have a whole bunch of vectors that point outwards that have a large magnitude. Further away from that charge, you'll have smaller vectors that still point in the same direction but have a smaller magnitude. And you could fill this in more detail if you want, but the point is the best way to visualize these things is to just draw a bunch of vectors. So we can learn a lot from this drawing, actually. Just by looking at this, we can learn a lot about what's happening, what type of charge it is, and things like that. So the strength of the electric field, and when I say strength, I really mean magnitude, diminishes as we get further from the source. And that's expected. And that's because the electric field decreases in magnitude with distance squared. What else can we learn? We also learn that it points away from the source. In this case, it points away because it's a positive charge. Also, there's a mathematical fact that you can maybe see by looking at this. It has zero curl. What that means is it basically doesn't curl in on itself. Like it doesn't go like this. And that's actually really important. Right, so no, so don't think of this as like pushing or sucking or whatever. Think of it more as just like emanating. And so for a positive charge, it emanates outwards. For a negative charge, it emanates inwards. That's all. So if we want to find the electric force, we can do it in 2 steps. So first, this is the electric force, say, between 2 charges. So one charge produces an electric field. And then the second step would be that another charge experiences or detects, or rather, it experiences a force due to the electric field. So really, what causes forces on charges is not the other charges, it's the electric field. Now, typically, the electric field is created by other charges elsewhere, but it's the electric field itself, it's the universe, which is one of the ways that you describe the universe is by its electric field. It's the universe doing stuff to the charges. Now, the other charges can influence the way the universe acts, but think of it as more of a separated thing. The information about one charge passes through the universe before it comes back out to the second charge. So into equations, we would write that the electric field from Q1 would be KQ1 over R squared times R hat. And then the force from Q1 on Q2 would be Q2 times the electric field produced by the first. So the important point is that more generally, given an electric field, any electric field, the force on a charge think of the field as the thing that transmits the force. The force on a charge is Q times E on a charge Q. So this is important. This says that all you need to know to figure out what forces are on your charges is what's the electric field where those charges are. How are those equations related? So the point is if you multiply this equation by Q2, you get the Coulomb force, which is what we wrote down initially. Remember that the Coulomb force is K times Q1 divided by, or K Q1 Q2 divided by R squared times R hat. So all we've done is we've separated out all of the information about the distance, the direction, the magnitude, all of those things, and shoved that information into the electric field. And then all you need to do now to find the force is to just multiply the charge of the thing that's experiencing the force by the electric field. That's it. That's all you have to do. Like the constant G in gravity. So no. So the electric field is not constant. That's the important point. The electric field changes with distance, just like how the gravitational field changes with distance. Zero curl. So it means that the So you guys learned about the curl in 21D, I think. It's the vector curl. It's an operation. It means that if you take the curl of the electric field, you get 0. And we'll talk about that in a lot more detail way later. I just wanted to throw that in here. Is the strength of magnetic field like the intensity of waves? So this is the electric field, but yeah, so the strength of the electric field is like the intensity of waves. Yeah, it goes like an inverse square law. And that's because we live in a 3D universe. Right, so I know that this is a lot. But the bottom line is all you need to know is the electric field. And then once you know that, you just need to know how much charge something has. And that will tell you what force the charge feels from the electric field. So I need you to separate in your mind. It's not that charges apply forces to other charges. It's that charges experience forces from the electric field. And it's also true that charges can influence the electric field. So if you separate those two ideas, now we can just start talking about what happens when you have this electric field to these charges. Or similarly, if I have these charges, what's the electric field that it produces? Because once you can separate those two ideas, you can actually do a lot more complicated things, which is why we're doing that. So let's just back up a little bit, or not back up, let's move forward a little bit and talk about field superposition. So we already talked about how you can find the force on a single charge from multiple different charges. We'd like to know how to find the field from multiple different charges as well, because if we want to use this method of computing the force by just multiplying the field by the charge, we need to know what the field is from multiple charges. So what if there are multiple sources of the electric field? Well, or multiple sources of this electric field, like let's just say you have a whole bunch of charges strewn out everywhere. What would be the electric field from like the total electric field from all of those charges? It turns out that it's relatively easy to find. You just add the electric fields. Add the electric field vectors at each point in space. Now it sounds like a tall task, but generally what we'll actually have is we'll have a formula for our electric field from, say, one charge. In fact, it's this formula here, and it'll be in terms of x, y, and z or something like that. And then you'll have another formula for a different charge, and then you'll just add those two formulas together, and that will be the electric field from those two charges combined. That's it. There's actually a good reason for why this works. So let's think back and think about forces. So for two charges acting on a third, the way that we find the force on the third is by adding up the force. We add up the force vectors, i.e. the net force on the third charge would be the force from the first charge on the third charge plus the force from the second charge on the third charge, right? That's just normal forces add, normal net force business that you've seen in Newton in like 9A. But now we have an understanding as to how that force relates to the electric field. So this could be written as Q3 times the electric field from charge 1 plus Q3 times the electric field from charge 2. Right? That just works. Like mathematically, this is just true. The force on this is just a definition of the electric field. You can think of it that way. And so we can factor, and we get that this is Q3 times the electric field from the first charge plus the electric field from the second charge. And bada bing, bada boom, that is the electric field from Q2 and Q3. It's just the combined electric field. So at this point, I'm going to tell you again, there will be a place in the lecture notes where there's an example that I will link you to in the lecture notes that you can either click on, or you might not be able to click on it. You might just have to go to it. But you'll just be able to go to that page, and there will be a worked example of finding the electric field from two separate charges. Yeah, sorry, Q2 and Q1. You're right. So, but once we can do it with two, good question, Rachel. If you can do it with two, you can do it with more, right? Generally, the net force on an object, say you have n plus 1 charges, then you would sum from 1 to n the force from qi on the charge that we're interested in. And that can be written as the sum from I equals 1 to n of the charge times the electric field from charge qi. And so we can factor that out. We get q times the electric field times the sum of the electric fields. And that's just equal to q times the total electric field, just E, without any subscripts. So Isha, it's not a bad question. The point I was trying to get at is because the forces are additive and the electric field is just proportional to the force, it's only related to the force by the charge that's feeling it, the electric fields also have to be additive. That's just a property, that's just because the forces are additive. Because if we want to find the net force, we have to add up all of the forces from individual charges. And because the individual forces can be written in terms of individual electric fields, those individual electric fields also have to add up so that when you multiply by the charge it's acting on, you get the total force. So this E here, this E that I've written, E with a vector, that is the electric field due to all of the other charges. It's not the electric field that includes the electric field of Q. It's the electric field that is everything else. Should I be thinking of the electric field as a gradient or like the function that the gradient is taken up? Think of it as the gradient of a function. And we will get to that, I promise. So that F net would be on Qn plus 1, precisely. All right, so just going to take another quick aside for a visualization or for visualizations. We're going to talk about field lines just for a quick minute. This is just another way to visualize vector fields. So rather than just drawing a whole bunch of tiny vectors, because they will get really tiny as you get further out, sometimes it's just useful to just join the vectors to form continuous curves. And it just makes them a little bit easier to visualize. So for a monopole, and I'll explain what that is in a minute, a monopole, literally meaning one charge, has field lines that look like the following. You have your positive charge in the middle. So let's go back and look at the what the vector field looks like. So all we're doing is we're just going to join up those charges, or join up those lines. And so what it looks like, what it ends up looking like anyway, it just looks like this. And we put the arrows in the middle to indicate that this is not a standard vector field visualization. It's a field line visualization. So that's what the field lines look like. That's what the field lines look like for a monopole. What about for a dipole? A dipole is a more interesting configuration. A dipole is when you have two opposite charges near each other. So the field vectors would look like this. You have a negative charge, say, which has all of its field vectors pointing inwards. And they get weaker as you go further out, right? And then you have the same thing, but a positive one next to it. Say over here. Has to be the same amount of charge, by the way, in order for it to be a true dipole. And then all we're going to do is we're just going to join them up, join up the lines, so then they form continuous lines. An important point about these field vectors is that they only start and end on charges. And again, we'll talk about that in more detail in the coming weeks, but that's an important detail. So the field lines then would look something like this. And I'm going to do my best to draw this well, but it's always hard to do freehand. So you'd have a line that goes, so you would join these two lines, right? Because that seems like it's continuous. Oh, come on, erase. That seems like it's continuous. So you'd have a line that goes like this. So there's still no curl. That's true. There's still no curl in the dipole. You have lines that go like this, lines that go like this, lines that go like this. Sorry, I don't want the arrow at the end. I want the arrow in the middle. Sorry, this is getting very blobby. And then you'll have lines that come out and they'll join up after they wrap around the entire universe over here. And then you'll have one coming in that literally wraps around the entire universe and goes out. So this is what the field lines would look like for a dipole. So are the two charges in a dipole locked together? No. So actually, typically they're separated, because they're kind of locked away from each other. Because if they were allowed to just freely move around, they would instantly come together, right? Because they're attracted to each other. The point is the charges in the dipole are kind of are a fixed distance away from each other, and then they form this configuration. Let me make this less terrible looking. There we go. That's less bad. So we can actually learn something from field lines in the same way that we can learn something from these vector field depictions. Obviously, we can learn about the direction. That's pretty easy, because like if you look at a point here, the direction is going to point that way, right? Because the direction of the vector points along the field lines. So it's not that something in particular is preventing them from touching, it's that they are prevented from touching by something external, right? Like just imagine that you have a charge here that's glued down and a charge here that's glued down. There will be some electric field configuration, and this is the configuration that it makes. If they were allowed to move together, though, they would. They're just not, because for whatever reason. And you can do this like in a lab. No, so I'm getting to that. So the direction of the field points in the direction of the field line. So it would point, if you were at this place, it would point like that way. It's not curved. Vectors always point straight. It'd point like that way. If you were here, it'd point this way, and so on. And the strength of the field, the strength of the electric field is given by the density. The density of the field lines. So what I mean by that is how many field lines are close, or at which places are the field lines closer together, and at which place are they further apart? Like if you look close to the positive charge, the field lines are all close together, right? Whereas if you look further away from the positive charge, the field lines are all further apart. So the strength gets weaker as the density. And it turns out there's an explicit relationship. The strength is exactly proportional to the density of the field lines. So the further apart the field lines are from one another, the less strong the force or the electric field is, the smaller the magnitude. Right, so this is just a convenient way to visualize fields. There's nothing like super technical about it. It's just nice and easy to do. So often we'll just draw, rather than drawing these vector depictions, we'll just draw field line depictions. So I wanted to just get that across before we continue. All right, now we have to take a detour back to 9A. Hopefully you guys remember this stuff. It's probably been a while. So do you guys remember when you took, and by the way, all of this will be written out in extreme detail in the lecture notes, but I'm just going to kind of gloss over it because it is technically review. You guys remember when you were finding moments of inertia for like continuous things? Like if you have a rod, you wanted to find the moment of inertia of the rod. Well, what you had to do was you had to integrate something because it's continuous rather than like just a few bunch of these. These are going to be posted. This will be posted. It's just a few, rather than just a few bunch of point masses that you would find by just adding up the moments of inertia of each one, you integrate. Oh, so everything that I'm writing now is a subset of the things that are posted. So it should be there. So if we want to figure out what the electric field is, say, from a particular, from some, say like 13 different charges, you just add up the electric field from each one of them. But what if you have like an infinite number of charges or an infinite number of infinitesimally small charges that are all distributed like in a line? Or maybe they're just, maybe this whole thing is charged, but it's not like a bunch of discrete charges. It's a continuous spectrum of, or it's a continuous charge distribution. It's an infinite sum. That's exactly the point. And so an infinite sum is just an integral, especially when you're summing over infinitesimally small things. So we are going to talk about continuous charge distributions next. So I did say earlier that there's actually a minimum number of charge, or a minimum charge size. This is E, the fundamental charge. Now, that seems to like contradict the idea that we can even do anything with like continuous charge distributions, because that requires infinitesimal charges, right? Not just small but finite. But for our purposes, that fundamental unit of charge is like orders of magnitude smaller than the smallest charge we will work with. So we can just treat it as if it were continuous, even though it's not. Like it's technically discrete. There's like a charge here, a charge there, a charge there, a charge there. But like they're small enough and close enough together that we can just treat it as if it was smooth and smeared out. So for example, let's say we want to find the electric field from an infinite line of charges. How would you do that? Well, you can't just do a finite sum. You have to do an integral. And so we're just going to use the same techniques that we used in 9a. So in 9a, for the moment of inertia, for example, for a rod or a one-dimensional anything, the moment of inertia, for a discrete number of things, you would sum over from 1 to n, and you would write mi r sub I squared, right? And then if it became a continuous rod, for example, or a continuous anything, the moment of inertia became an integral. And it was r squared dm, because the mass became infinitesimally small. And then you could do a trick where you rewrite that small chunk of mass. Well, you write it in terms of some coordinate. So maybe it becomes r squared of x times, so x is the variable that we choose, and then dm becomes lambda, it becomes, say, lambda dx. So we're going to do a very similar thing here. So in that case, we ended up, we wrote that small amount of mass as a small length of the rod times a density. In this case, it was linear, or it was a mass per unit length, or a linear mass density. And so that was a way to convert this small amount of mass into some spatial distribution that we can then add up over using coordinates. And so we're going to do the same thing for electric fields. We're just going to add up the contribution of an infinite number of infinitesimal charges. So the equivalent thing would be, initially, you have a sum over some finite number of things. This would be the kqi over r squared times r hat. Remember, this is just the electric field for a single charge. Where is it? See here. And then you'd add up the electric field from a whole bunch of them. That becomes, once it becomes a distribution, maybe over a line, I'm going to put line here. The electric field, again, integrated over a line, becomes k times dq. So in this case, charge plays the role of mass. We still have to divide by r squared and multiply by r hat. It's because I tried to open up Chrome on accident. There we go, should unfreeze. There we go. Over a line, maybe it would be k times lambda dx over r squared in the r hat direction, where lambda now dq is equal to lambda dx. This is just an example. It'll get more complicated, but the point is we can now just like how we could describe mass as a distribution across positions, we can also describe charge as a distribution across positions. And in fact, it doesn't even have to be constant. You can have, maybe I have charge distributed along this pen. Maybe I have more charge over here and less charge over here. Then lambda would be bigger over here and smaller over here, right? So you I hate this. Sorry, guys. Well, I think that you guys can actually hear me. I think it's just my Zoom dropped. So I'm going to keep going because it's still recording, at least I think. So, and if it comes back and it didn't record, then you'll see the lecture notes. Right, so you guys have all taken one-dimensional problems because you guys only knew how to do one-dimensional integrals, but now you know more. So we can do all types of integrals now. We can do lines, like you've already done. In that case, dq, oh, I'm back. In that case, dq is lambda dl, right? So you, and I'll draw a picture for this in a minute. And so in this case, lambda is charge per unit length. We can also do surfaces. In that case, you have charge smeared out over a surface. So we need to integrate a two-dimensional thing. And so the measure, rather than just dx or dl, it has to be dx dy or dA. This would be sigma dA. And here, sigma is charge per unit area. And then we can even go far to volumes. Here, we would have dq, charge smeared out throughout an entire volume of something, like throughout not just the surface of the pen, but the inside of the pen too. That would be rho dV. And here, rho is charge per unit volume. So all of these things over here, these are charge densities. It'd be line charge density, surface charge density, volume charge density. They basically tell you how much charge is in a specific region of the correct dimension. So if it's a line, it would be one-dimensional, so it'd be a line charge density. How much charge is in a specific length? If it was a surface, it'd be how much charge is in a specific area, a specific size square, and so on. So in the linear case, maybe you have a whole bunch of charges, but they're lined up in like some squiggly way. In that case, this little length here, a little length there, that would have length dl and have charge dq, which is equal to lambda dl. For surfaces, I'm going to get rid of those labels. For surfaces, you just have, some sheet. And maybe you have some chunk of area, dA, and it would have charge dq. That small sheet would have charge dq, which is equal to sigma times dA. And you would add up the contribution from all of those individual sheets. For a volume, and I'm going to try my best to draw a lumpy thing. Hard to draw three-dimensional. You would have a chunk of volume here, which has a volume dV. You have to imagine these are infinitesimally sized, and it would have that small volume would have charge rho dV. And then you would add up the contribution from all of those chunks of charge. Now, just as a quick aside, quick note, dq has units of coulombs, right? It's still just some amount of charge, even if it's infinitesimal. And so the units of lambda has to be coulombs per meter. The units of sigma has to be coulombs per square meter. And the units of rho has to be coulombs per cubic meter. So that's just a quick check that all of the units do make sense. So what is the total charge on the line above? What's the total charge here? Well, the total charge would be what you would get if you added up the amount of charge on each individual chunk, and then or if you took the charge on each individual chunk and added them all up. So the charge would be capital Q. This is total charge, and that's always the letter we use for total charge of a thing. Total letter. Total charge. That would be equal to an integral over the line of lambda dl. For the surface, the total charge is an integral over the surface of sigma dA. We're just adding up the charge in a small square times its size, and then you do an integral for that, for integrating or adding up all of those little squares. For a volume, it's exactly as expected. It's a volume integral. It'd be rho dv. So it's actually, like, you guys all have the math now to do these integrals, so it should all be entirely doable. Now, you might ask why this works, like why we can just break it up into infinitesimal chunks and then add them up. But it works for the same reason that it worked for moment of inertia in 9a. And the reason is that because we're making it infinitesimal, its shape doesn't matter anymore. You can just treat it as if it were a point charge. And then you just add up the contributions from all of those point charges, and the shape of the object overall will come into play by how those point charges are arranged next to other point charges, the infinitesimal point charges. So basically all we do is we just treat the individual, we treat each of those infinitesimal charges, either a small chunk on a line, or a small square on a surface, or a small blob in another blob. We just treat those as point charges, and then we know the electric field from a point charge. It's just k times its charge divided by the distance squared times the unit vector. Like that is the electric field from a point charge, and then you just add them all together by doing an integral. So I'm going to start an example that we're not going to have time to finish. This example is linked in the lecture notes. I think that this example is also covered in the LibreText, but I'm not going to do precisely that example. My numbers will be a little different. But it's a very standard example. So I'm just going to start it and we'll continue with it on Thursday. So let's actually do this just so you can see how it's done. We're going to ask, what is the electric field a distance r from a charged straight line segment of length L. So the straight line segment has length L and total charge Q. And we're going to assume that the charge is evenly distributed, just because otherwise it's harder. It's still doable, but it's just harder. Right, okay, so let's draw a picture first. So we have some line segment, some rod has length L. Why can't I? There we go, has length L. And we are interested in, for the sake of symmetry, we're going to assume that the point we're interested in finding the electric field of is a distance r away, and it's r away from the center of the rod. And so we have a whole bunch of charges distributed along this rod. They're uniformly distributed, and for the sake of argument, I'm going to say that they're positive, but everything works out if they were negative because the sign would correct for that. Basically, I'm assuming that the total charge Q is positive, just so I can draw positive charges, but it doesn't actually matter. This is just for the drawing. So I'm gonna fill out this drawing as we go, but let's start by just talking about it a little bit. So uniform means something very special here. It means that a chunk of length L, a chunk of our rod, lowercase l, has charge. It means that it's proportional to the length, right? Charge, say, Q, which is lambda L. So lambda is just some constant of proportionality in this case, because it's uniformly charged. So if you double the length of your chunk, then you have twice the charge. And so we can actually learn something in particular about this. In particular, for the whole rod, the charge is Q, and the length is L, which tells us that this constant of proportionality is just Q over L, which is helpful. It tells us what the linear charge density is. Super useful thing. And also, if we had some infinitesimal slice of charge, like, say, a very, very narrow slice of the rod here, the charge of that very, very narrow slice would be lambda times dl, where dl, oh, I hate that it like automatically deletes things. It's very annoying. This little tiny slice has length dl, and it has charge dq. Now, we need to figure out a way to describe the location of that charge in terms of some coordinate. Because we want to be able to do an integral, and at the end of the day, we need to put coordinates on things to do integrals, right? So let's just figure out let's just slap on some coordinates and call it a day. Let's call this direction the positive y direction. Let's call this direction the positive x direction. Let's call this line here, let's call it y equals 0. And our small chunk of charge, we're going to say that it's at position y. And now we're done. Like, oh, and by the way, we're interested in the electric field at this point P. So those are the coordinates that we can use. So in these coordinates, instead of using dl, well, how far do you have to go in the x and y direction in order to produce a length that has a length of dl? Well, you have to go up an infinitesimal amount in the y direction. So in that case, dl is just equal to dy. If you move a small distance in the y direction, you get something that has small length dl. Again, you guys have seen this sort of thing before in 9a, but hopefully now having seen 21D, hopefully now it's all a little bit more, you understand it a little bit better. Oh no, am I still frozen? Am I still frozen? Oh boy. Well, again, it's still recording, so it should catch up in a minute. Now, as an aside, we are interested in the electric field at that point P, but the electric field is a vector at that point. It's not just a vector field, it's just a vector because it's only at a point. And so this is equal to the x component of the electric field plus the y component of the electric field. And I'm suppressing the z component because we don't have to worry about that here. But it should be the same. It would be the same cylindrically around it, right? Did it unfreeze, by the way? Maybe? Testing? The video is still good, but it's not good. All right, well, I'm gonna stop here then because it froze and I don't want to I don't want it to I don't want to get too far ahead. And anyway, we're near the end of lecture. Maybe I'll just start lecturing on my wife's computer. It's faster, or it's less bad than this one. How many of you guys are yelling on the Discord? None. That's surprising. Well, I can't see any. I can't see anything. Like my whole. Well, this is going to be the end of lecture anyway, so I guess we'll just. Oh, wait a minute! I'm back. I'm back. Am I back? Okay, looks like I'm back. Although my machine just went to rotating circle again, so maybe I'm not back. I was back for a sec though. All right. Well. This is the end of lecture. I'm going to try to end the recording. I actually have to wait for it to come back. I actually have to wait for it to come back before I can end the recording. Otherwise, it might not actually upload, which would be very bad. I think I'm going to upload the lecture notes shortly, actually. And in fact, this whole example is going to be uploaded, and I'm just going to rehash it on on Thursday, I'm gonna continue where I left off on Thursday with this example. But this whole example, I'll just upload the entire thing, so then you guys can take a look. Oh boy. All right. Will it? Oh, idea. End my stop video. Maybe that'll work. Yeah, because I can't see the chat at all. Oh, okay. Ending. Oh, no. Okay. So I'm just gonna disconnect from. I'm just gonna disconnect from Zoom and hope that the recording is saved.